All right, so let's review regression. Let's start out with simple linear regression and talk about what you need to know. So if you remember, the simple linear regression equation is an equation that describes how the average value of y changes with individuals' x values. So the equation says that the average value of y at a particular value of x is just given to you by beta 0 plus beta 1 times x. Or in other words, the average value of y has a linear relationship with x. It's just an equation for a straight line. So what are beta 0 and beta 1? Well, those represent essentially the truth. These are the quantities that we wish we knew, but we never will because we only are having a sample. Beta 0 and beta 1 would be the line that best describes what's going on with the entirety of the population if you happen to have data on every single individual out there. So we call beta 0 and beta 1 the true coefficients, and our job is to try to estimate them from just a sample. Okay, one of the key things, and one of the things you'll be graded on actually quite a bit, is the interpretation of the slope. The intercept here, really not all that important. That's just the average value of y when x is equal to 0. But who cares about x is equal to 0? That's rarely an important quantity. It's the slope that really ties in x and y together. So here's what you're going to need to do. You're going to need to be able to interpret the slope in the following manner. I'll tell you to, hey, finish this sentence. Two individuals whose values of ... and you'll need to take it from there. So how do we interpret the slope? Well, we say that two individuals whose values of x differ by 1 unit are expected to differ in y by beta 1 units for whatever reason. And so here I'm annoyed at myself because I have a typo right here. Two individuals whose values of x differ by 1 unit are expected to differ in y by beta 1 units for whatever reason. If beta 1 is positive, the individual with the larger value of x is expected to have the larger value of y, etc. So make sure that you can interpret the slope and not leave out a key thing like I just did. Okay, one thing the slope does not tell you is what would happen to an individual if his or her x value changes. Regression-like correlation is not a statement about cause and effect, and this is one of the least understood and most misinterpreted things about a regression equation. People seem to think that the slope indicates that, hey, if my individual value of x goes up by 1 unit, that means that my y value is expected to change by the slope units. No, that's not the case. The slope only tells us how we expect the averages of two groups or two individuals to differ. Not the same individual. It doesn't tell us anything about what happens to an individual's y value if its x value increases by 1 unit. Key thing to remember, don't forget that. So, for example, here's our equation relating salary and education together. We've talked about this at length. The slope is 128. So, how are we going to interpret this? Well, what we say is that two individuals that differ in education by 1 year are expected to differ in salary by $128. Since it's positive, the person with more education is expected to have the higher salary. Notice that I took this interpretation here and I replaced x, unit, beta 1, units, etc. by the context-specific words. On the exam, do not leave your interpretation in terms of x, y, and units. You're not going to get many points for that. Make sure to interpret it like I just did with this example. All right, so that's a great equation. We can interpret it. We can talk about how it describes the relationship between x and y. But how do we get the best line? How do we get the line that goes through the points the best? Well, there's actually a lot of ways to do that, but what we will use is the least squares criteria. So this is an important thing to know. How does the least squares criteria operate? Well, what the least squares criteria does is it wants to find the line that minimizes the sum of the squared residuals, or alternatively the sum of the squared errors. What's the residual? Well, that's the difference between the actual value in the data and the value predicted from the line, or in other words, the distance between the line and the actual individual. So if we square that value and then sum that up over all individuals, that's our sum of squared errors. The least squares criteria produces the line that has the smallest sum of squared errors. Okay, a note about notation. I kind of touched on this already. Beta 0 and beta 1 represent the truth. Basically, if we had data on every single individual in the population, this would be the intercept and the slope that we would measure for their least squares regression line. Now, we only have a sample, unfortunately, so when we estimate these quantities from the data and find the least squares regression line that best fits the data, we're going to call the intercept and the slope B0 and B1 to represent that those are just our best guesses. Now, we know that what we measure is never equal to the truth. It's going to be off by a certain amount. The typical amount by which we think our estimates are off are what we call the standard error of the estimates. And we think that our best guesses are going to be close to the truth, but they'll probably be off by a standard error or two. More on that in a little bit. Okay, so we make a line relating the average value of y to x. We would like to know, is our regression statistically significant? All right, so what does it mean for a regression to be statistically significant? Well, regression is all about minimizing the sum of squared errors, so it makes sense to base our criteria for significance on what the sum of squared errors actually is. And so what the procedure does is it compares the sum of the squared errors for the naive model to the sum of the squared errors using the regression. So what is the naive model? Very important for you to know. Well, if this is my scatter plot between y and x, the naive model says, hey, x doesn't tell me anything about y at all. I'm just going to predict y from the overall average value of y in the data, regardless of what x is. So the naive model is a horizontal line placed at the average value of y. And if we calculate the sum of squared errors, basically look at the distance between this line and the point, square up that distance to get the squared error, sum them all up, here would be the sum of squared errors from the naive model. The regression line, well, we find the line that minimizes the sum of squared errors. Its sum of squared errors is 174. And so what we see is that the sum of squared errors has been reduced actually by a substantial amount. A regression is going to be statistically significant if the reduction when going from the naive model to the regression is large. In other words, unlikely to have been produced just by random chance. So what does it mean to be produced by random chance? Well, the sad fact is that even when we use a completely unrelated random predictor to predict y, that's always going to fit the data better than using the naive model. Because a line, it has a slope, it has a little bit more wiggle room to fit the data better than a flat horizontal line. So there's always going to be a sum of squared error reduction when using any old predictor. In order to be statistically significant, the reduction needs to be big, larger than what you would expect by chance. So that's what I just said right here. So how do we figure out what kind of reductions in the sum of squared errors just happen by chance? Well, same thing as we've been doing for all other tests of significance, we can run a permutation test. We can randomly pair together the x and y values, thereby, by design, breaking any sort of an association or relationship they have, and then find the least squares regression line on that permuted data set. We can calculate the reduction in the sum of squared errors that it's able to achieve, and repeat that again and again and again and again to build up a distribution of possible reductions that happen just by chance alone. So the p-value of the regression is going to be the fraction of those permuted data sets which just happen to achieve at least as large a reduction in the sum of squared errors as our regression. And so if that p-value is small, less than 5%, it's highly unlikely that chance alone would be able to yield such a large reduction in the sum of squared errors. So we say that, yeah, our regression is statistically significant. So when the regression is statistically significant, we say that, hey, our regression is predicting y better than the naive model. Basically, we gain information about y from using x to our advantage. Okay, here's just a small illustration of the naive model versus the regression, what the sum of squared errors are, what the reduction is. We can skip this. Here are some permuted data sets where we randomly mix up the ordering of the y's and calculate the sum of squared error reductions. and then look at the sampling distribution, the possible sum of squared error reductions from random unrelated predictors. And we see the sum of squared error reduction measured from our sample is highly out of line with what would happen by chance. It's not impossible to happen by chance, but so unlikely that we would say it's statistically significant. This p-value, in this case, 2%. Only 2 of the 1,000 permuted data sets achieved a sum of squared error reduction at least as big as what we measured. Okay, so classic statistics before computers, they used a special assumption about the distribution of the residuals, namely that they were normally distributed to come up with an approximate p-value for the regression. We're not going to worry about where that really comes from. We just know that if that p-value is less than 5%, the regression is statistically significant. It's unlikely that a random predictor would have reduced the sum of squared errors by at least as much as your regression. Your regression really is predicting y better than just the naive model, not using any information about x at all. So is it practically significant? Well, we check r squared and the root mean squared error as a follow-up. Okay, speaking of that, what is the root mean squared error? A key term. The root mean squared error is the typical size of the residual. In other words, how far points typically are away from the line. So what's a big root mean squared error? What's a small root mean squared error? Well, that completely depends on the context of the problem. So it's up to you to decide. Look to see how variable the y values are. Compare that to the root mean squared error and see, okay, well, are you obtaining significantly more accuracy, at least in your opinion? So remember, R calls the root mean squared error the residual standard error. Not to be confused with the standard error of a coefficient, which we will address shortly. All right, r squared is another thing to gauge practical significance, and r squared gives the percentage reduction in the sum of squared errors when we use the regression model instead of the naive model. So r squared goes from 0% to 100%, the larger the better, but once again there's no arbitrary cutoff that says, hey, an r squared bigger than this percentage means your regression has practical significance. That's always going to be context dependent as well. So r calls r squared the multiple r squared. Okay, so we get our least squares regression line. We measure a slope and an intercept. These are the true values that we'll never know. We measure b0 and b1. And what we'd like to know is, since we know that what we measured isn't equal to the truth, how far off is our measured slope likely to be from beta 1? Well, to make that sort of inference, we actually need to develop the full regression model. We need to say something about how individual values of y are related to x. So here's our full regression model that says an individual's value of y is just beta 0 plus beta 1 times xi. This component right here is just the average value of y, plus a disturbance. So this disturbance represents how far away the individual is away from average, either above or below. And we make the key assumption that the distribution of possible disturbances is normal, with a constant standard deviation, meaning that typically individuals are about the same distance away from the line, no matter what their characteristics, no matter what their x values are. So visually, this is what we assume. So if we took a small slice at a particular value of x, the individuals don't all fall on that regression line. But the distances they are away from the regression line, the distribution of the residuals is normal. And it's the same normal curve no matter where we look. That's the key assumption of the regression model. All right, so when those assumptions hold up, we can actually talk about how far off the measured slope is likely to be from the truth. Well, the number that we come up with is what we call the standard error of the slope. The standard error tells us how far off we expect our measured slope is likely to be from the truth. It's the typical distance between what we measured and what the truth is. So, key difference, the standard error of the slope is kind of a measure of uncertainty regarding the slope of the regression. The root mean squared error of the regression is a measure of the typical prediction error that it makes on the data set. All right, so once we have the standard error, how far off we think what we measured our slope might be from the truth, we can actually make a confidence interval to come up with a range of plausible values for what the true value beta 1 might be. And in fact, it turns out that when all the assumptions are met, about 95% of random samples turn out to have their measured slope be at most 2 standard errors away from beta 1. Kind of a neat thing that pops out of statistical theory. So that tells us, hey, take our measured slope and go about plus or minus 2 standard errors away, and that range of values is going to have about a 95% chance of getting it right and actually covering beta 1. So our 95% confidence interval is to go and take B1 and then move plus or minus about 2 standard errors away. This will give us an interval with approximately 95% confidence. So, what does 95% confidence mean? Another key thing that you definitely want to know for the exam. What does it mean to have 95% confidence in an interval? All right, so confidence refers to the long-run fraction of time that the procedure yields a correct interval. So if we were to go take a new random sample, our confidence interval is going to be a little bit different because our slope is going to be a bit different as well. So in the long run, what's going to happen is, oh, and I wish I had this slide. If you remember the slide that had all the confidence intervals, some were red, some were black, some got it right, some got it wrong. That was what I was illustrating what confidence was. Basically, sometimes the confidence interval gets it right, sometimes the confidence interval gets it wrong. You'll never know which ones are right or which ones are wrong, but in the long run, 95% confidence intervals get it right 95% of the time. So, what does it mean to be 95% confident in an interval? That means that we're 95% confident in the procedure that generates the interval. In the long run, 95% of the time that we make one of these confidence intervals, we get it right. Okay. We can also use the regression model to make predictions, but there's two types of predictions we might be making. We might be trying to predict the average value of y among all entities with some common value of x, or, and this is usually what we're trying to do, predict an individual's value of y who happens to have a particular value of x. The point estimate is the same, just plug in the value of x in the regression equation, but the standard error, the amount of uncertainty we have with the prediction, is different. So here's the formula. Here's some key bits on how much uncertainty we have with our prediction, how that varies based on the amount of scatter in the stream of points, how spread out the x values are, how far away we're predicting from the average value of x. You should know all these things. But one of the key things is that the standard error for an individual's value of y, this is the standard error for the average value, is always going to be bigger because individuals differ from the average by a random amount. So the key thing to remember is that there are formulas that tell you how far off you think your estimated predicted value is from the truth, and they depend on a few of the characteristics of the data itself. But if you're trying to predict an individual's value of y, that's harder than predicting the overall average, because who knows how far off that individual is going to be away from average. Its standard error is going to be bigger. So we differentiate between those two predictions by calling the two intervals, well, range of plausible values, slightly differently. So the confidence interval is always for the average value of y at a particular value of x. The prediction interval is for a particular individual's value of y. So the interpretations are a little bit different. You just want to make sure to be able to identify which interval, the confidence or the prediction interval, you need to be using based on the context of the problem. If you're predicting an average, confidence interval. Predicting an individual, prediction interval. Okay, one thing to be careful of is making extrapolation. It's not okay to make a prediction at a value of x that's outside the range of x's used to build the model. We have no guarantee that the relationship is going to continue to be linear outside the range of x that you used to build the model. And so if you make a prediction there, that is extrapolating. You may end up getting it right, and that's great, but there's no guarantee, there's no statistical guarantees at least, that any of the confidence intervals or prediction intervals will be correct. All right, so one key thing in regression modeling is checking the assumptions. So all of the formulas for the standard error, the confidence intervals, the prediction intervals all hinge on the assumption that the regression model is an accurate reflection of reality. In other words, we have a linear relationship between the average value of y and x, and individual values of y differ from the average by a random normal amount. So, key thing, you want to be able to make sure you can check the validity of a regression model by doing statistical and graphical assessments. We need to make sure that the relationship is linear enough. We need to make sure that the vertical spread of the residuals is the same everywhere. And we need to make sure that the overall distribution of residuals is normally distributed. If any of these is violated, well, we can't use the regression at all. So how do we visually check this? Well, we look at the residuals plot, the plot of the residuals versus the predicted values. So basically the error the regression makes versus the predicted value of y. A good residuals plot has no interesting patterns left over. Basically, all the interesting stuff about x and y are explained by the regression, so when we look at the leftovers, the left errors, there's nothing interesting. So good residuals plots look like this. Remember, it's okay to have kind of unequal horizontal density here. You can have gaps. That's fine. That's just a reflection of how the x values were collected. But if you have unequal vertical spread, that's bad news. That's a deal breaker. If you have curvature, that's a deal breaker. There's something left over that your model's not explaining. If you have obvious non-normality with extreme outliers like this, that's bad news as well. So careful not to overinterpret the patterns. We talked a little bit about that. A little bit more about QQ plots, gauging normality. It's sort of hard from the histogram of the residuals. A good QQ plot would look something like this, where most of the points are inside the upper and lower dotted bands, maybe a little bit kind of outside the bands at the left or the right here. That's fine. But something that would be bad would be having a lot of points outside the upper and lower dotted bands and a consistent monotonic curvature in the stream of points in the QQ plot. So be careful. Make sure you can interpret one of these guys. All right, so how do we actually check the validity of the regression model? Well, step one, we actually look at the statistical test of the assumptions. And for each test, what we would like to see are p-values that are 5% or greater. Remember, a p-value less than 5% says statistically significant, tells you something interesting is happening. With residuals plots, we don't want to see anything interesting happening, so we want p-values 5% or bigger. So if they all pass, we're good to go. If some are failed, well, let's look at the sample size. If we have 25 or fewer data points, stop. You need to abandon the model. You just can't use it. If you have more than 25 data points, look at the diagnostic plots. If there are obvious violations of the assumptions, you need to stop. The model's bad. If those violations are small, if you can't even see them, well, you're good to go. These tests get very, very sensitive for large sample sizes. Okay, so make sure you can check the validity of a regression model. I will ask you about that. Finally, what do we do if our model's bad? Well, we know that we can employ the method of transformations. What we call x and what we call y are arbitrary. They can be what we measured in the data, or they can be transformations of what we measure in the data. So what do you need to know about this? Well, you're going to kind of look back to one of those homework or the activity problems where you look at the output of find.transformations. So I want you to be able to look through a list of proposed transformations to determine which one is the best, essentially the one with the highest R squared. And then also tell me whether or not there is really any difference between some of the members of that list, or even if the transformation is better than just sticking with the original values. So remember, if the R squareds are within 0.02, then statistically it's really just about the same thing. One model's performing about the same as the other. So it's only when the R squareds are different by about 0.02 or more can we really say that one transformation is better than the other. Okay, and I just got a text that UT is completely closed today, so I'm glad I'm recording this lecture. We're still having the exam on Wednesday or Thursday, hopefully. We'll see how it goes. Okay, so once we have the correct transformation, I'll give you regression output in the terms of predicting y.trans from x.trans and be able to untransform. So rewrite the equation in the form y equals ... So go back and look at homework 5 and activity 5 where I had you do this activity. Guess what? It's going to be on the exam. Okay, multiple regression, which we kind of discussed last week, basically allows us to incorporate additional information into our regression model. In business analytics, we're not trying to predict y from just one predictor variable. We have a ton of information we'd like to use. So that's what multiple regression allows us to do. It allows us to incorporate the information from a lot of different predictors. And even more importantly, it allows us to really isolate the association between y and a particular value of x after accounting for other information. So there are a few motivating examples where we were really interested in isolating the association between, say, someone's salary and their experience, or someone's GPA and their race. But we saw that really looking at these associations was tricky because in order to really do the association justice, we needed to account for all the other sources of variability in salary or variability in GPA. So regarding salary, we know salary depends on someone's experience, which is what we're interested in looking at, as well as someone's educational level and the number of months they've been working at the company. So in order to really gauge how salary and experience are related, we need to first account for the variation in salary that's due to education in months. So multiple regression allows us to do that. Throw education in months into the model, then look at the coefficient of experience. All of a sudden, you now have a much better idea of how salary and experience are related. Likewise, we know that different races have different GPAs. Some ethnic minorities have a noticeably lower overall GPA in high school and in college than other races. And we'd like to get to the bottom of that story. Is there really an inherent difference between capability and race? Well, probably not. But to make sure, we need to run a correct multiple regression. We need to account for all the other sources of variation in GPA before we really look at the association between GPA and race. So that means throwing into our regression model information about socioeconomic conditions, involvement of the parents, quality of the curriculum. There's a tremendous amount of different factors that can potentially explain variation in GPA, but we would need to account for all those sources of variation before really honing in on the relationship between GPA and race. But multiple regression allows us to do that. All right, so what is the multiple regression model? Well, it looks like the simple linear regression model. We just have a lot more predictors in it. Basically, an individual's value of y is a weighted sum of the predictor variables plus a disturbance. Remember, this disturbance just tells you how far off the individual's value is from the overall average at that combination of x. And once again, we're going to assume something special about the distribution of the disturbances. They are normally distributed. So typically, individuals differ from the overall average by the same amount, regardless of their characteristics. Once again, the graphical assessment of the assumptions of this is critical, so make sure you can do that. Same procedure as it is with simple linear regression with the addition of a few additional plots. The the residual versus predictor plots. We need to make sure that there's no leftover relationship between the residuals and each one of those predictors here. So here's the residuals plot, residuals versus predicted values. For the salary example, residual versus education, residual versus experience. We need to make sure there's nothing interesting whatsoever that's left over. Okay, so we talked about checking those plots. Very important key point right here. How do we interpret the coefficient in a multiple regression model? This is on the exam, and I expect you to completely nail this. This is one of the most misinterpreted things in all of statistics, even by professionals, and I want to make sure that you can do this correctly. So, all right, we get the coefficient of our predictor xi out. Let's call it beta I right here. How do we interpret it? Well, what we say is that two individuals that differ in xi by 1 unit, but whose other values of the x's are identical, are expected to differ in y by bi units. If bi is positive, the individual with the larger value of x is expected to have the larger value of y, etc. So, key thing, always replace x, y, units, b, etc. with context-specific numbers and words, but be able to reproduce this. So let's look at an example here. Here's my equation relating salary to education, experience, in months, and the coefficient of education is 93. All right, so if this was an exam and I said, hey, interpret this coefficient, what would you say? Well, you would say that two individuals that differ in education by 1 year, but who are otherwise identical, in other words, who have the exact same values of experience and months, Well, those two individuals are expected to differ in salary by $93. Since this is positive, the more educated individual is expected to have the higher salary. So that's a lot more words than what I'd actually expect. This is what you would actually say. You would say that two individuals who differ in education by 1 year, but whose experience in months are identical, are expected to differ in salary by $93, with the more educated person having the higher salary. So that's how we interpret the coefficient. It's very specific. It's very precise. It tells us something interesting about the relationship between salary and education after accounting for differences in people's experience in months. Okay. Once again, the coefficient does not tell you what happens to an individual's y value when their x value increases or decreases. It's really comparing two groups of individuals who are completely identical with respect to the other variables in the model, except they differ in xi by 1 unit. Okay. So, we got that. One thing that we do see with multiple regression, and this is why people get confused with the coefficients a lot, is because when predictors are highly correlated, the values of the coefficients can actually change dramatically between models, and sometimes they can have signs which look odd. So one of the key things in multiple regression is understanding that coefficients are model dependent. If you change the variables in your regression model, the coefficient of a particular predictor is going to change as well. So for instance, trying to predict body fat from someone's neck circumference, we see a coefficient of 1.6. All right, two individuals who differ in neck circumferences by 1 centimeter are expected to differ in body fat percentages by 1.6%, with the one with the thicker neck having the higher body fat percentage. All right, well, if we predict it from neck and abdomen, the coefficient is model dependent. Now all of a sudden the coefficient is negative. Two individuals that differ in neck circumference by 1 centimeter, but who have identical abdomen circumferences, are expected to differ in body fat percentages by 0.9%, with the person with the thicker neck having the smaller body fat percentage. Seems counterintuitive because we know that typically people with thicker necks tend to be heavier and have more body fat. However, this doesn't mean the model is wrong. It's actually telling us something interesting about the way the body probably works. So remember, what we're doing when we're interpreting the coefficient of neck is we're imagining individuals with the exact same abdomen sizes. Okay, well, among people with the same abdomen size, it looks like people with larger necks tend to have smaller body fat percentages. How could that possibly be the case? Well, maybe it's the case that if you have the same abdomen size as someone else, but you have a thicker neck, the only way for that to happen is to have a very muscular neck. And the more muscles you have, well, the smaller your body fat percentage. So maybe this makes sense after all. So key thing is, all right, the coefficient of your predictor variable is going to change when you add or subtract predictors out. And that's to reflect the fact that the coefficients are model dependent. The interpretation of that coefficient is comparing two individuals who are identical with respect to what other variables are in the equation, but differ in that value of x by 1 unit. So if you change the set of other variables, you're changing the set of individuals who are being compared to one another. So not too surprisingly, the difference in the average value of y is also going to be potentially different. Okay, so coefficients are model dependent. When we deal with multiple regression, in order to gauge how well the model is fitting the data, we need to use R-squared adjusted. Because R-squared has this unfortunate property that when you add even completely random, unrelated predictors, R-squared is always going to get bigger. So R-squared doesn't necessarily give you a good idea of how well your model fits the data. R-squared adjusted penalizes the value of R-squared based on the complexity of the model, based on the number of predictors in it, and so it gives a much fairer assessment of the model's fit. Okay, the root mean squared error does something similar actually. It also penalizes for the number of predictors, so you can use the R-squared adjusted or root mean squared error to gauge how well your model is fitting the data. Okay, what about significance in multiple regression? Well, the significance of the model is the exact same thing as the significance in simple linear regression. Does the model predict y any better than the naive model? We know that a model even full of random, unrelated predictors is always going to give a sum of squared error reduction compared to the naive model. the question becomes, is that reduction in the sum of squared errors statistically significant? We can get the p-value the exact same way. Basically, a model is statistically significant if the reduction in the sum of squared errors that it achieves relative to the naive model is unlikely to be produced by a model using an equal number of predictors unrelated to y. So same sort of deal. Not that interesting. We already know that. What about the significance of a individual predictor? Before moving on there, where do you get the significance of the model in multiple regression? It's right down here, this very last line. Okay, significance of predictors. Another very key important part. I want you to make sure that you know this, because this is also one of the most misinterpreted things in all of statistics. Okay, so we can find the p-values of individual predictors over here. So what do these p-values tell us? Well, if the p-value is less than 5%, it's statistically significant. But what does that mean? It means something very precise and actually doesn't actually tell us all that much. So here's the box quantity. An individual predictor is statistically significant if the reduction in the sum of squared errors when it is added to a model that already contains all the other predictors in it is large. In other words, unlikely to be produced by adding a random unrelated predictor to y. So when we gauge the significance of an individual predictor, we're imagining a model that already has all the other predictors in it. We add in our x variable and we look to see how much of that sum of squared errors get reduced. Did it get reduced by more than what we would expect just by random chance? If it did, then we say it's significant. Or in other words, adding x into that model with all the other variables in it significantly increases the amount of information about y in the model. All right. So significance is also model dependent. Here we're predicting the number of wins of an NFL team by the number of offensive total plays. We see that it is statistically significant. That's great. All right. However, in a model with offensive total yards, it is not significant because the p-value is now 17%. So what gives? Is this a contradiction? No, it's not. Because the significance here is model dependent. What this is saying is that when we add offensive total plays to a model that already contains offensive total yards, the additional reduction is small. It's likely to occur just by random chance. So in other words, whatever information that offensive total plays has about wins is redundant with the information already provided by offensive total yards. The information or the amount of additional information offensive total plays provides above and beyond what the total yards already gives is not significant here. Okay, so there's a much more detailed explanation if you need it. So another example with body fat where we see that, hey, the model's significant, but none of the predictors are significant. That just means that adding an additional variable into that model when the other two are already in there never yields a significant reduction. Basically, we only need 2 of these 3 predictors. So what do you need to know? You need to know that significance is model dependent. X may be significant in a simple linear regression, but not in a multiple regression. Well, X contains useful information about Y because it was significant, but what that means is that the amount of additional information above and beyond the info provided by the other predictors in the model in the multiple regression is not significant. In other words, the info provided by X is redundant with the information provided by the other predictors. The reverse may happen. X may not be significant in a simple linear regression, but it is in a multiple regression. All right, what gives? Well, X really does contain useful information about Y. It just means that in this case, the amount of variation in Y due to other factors not accounted for in the simple linear regression is overshadowing the variation in Y that can be attributed to X. Basically, the association between Y and X is getting washed out by much stronger associations between Y and other predictors, like the starlight getting washed out by the sun in the daytime. And it's only when we have a multiple regression model and we can account for the variation in Y due to these other predictors does the association between X and Y stand out. And that's what we saw with the experience example. By itself, experience is not a statistically significant predictor of salary because so much of the variation in salary is actually due to education. Once we account for education and add experience to the model that already has education in it, yes, experience is statistically significant because now all of a sudden we can see the effect, the association between salary and experience. So experience alone is not enough to determine what someone's salary really is. However, the amount of additional information provided by experience once we already know education does give us a little bit of additional information about salary. Okay, we know that if we have a non-significant predictor, we can drop it from the model because it doesn't add anything above and beyond what the other predictors are already telling us. So we can always drop one predictor without losing anything. But we can't drop more than one predictor because p-values are model dependent. And if we were to drop one predictor, all the other p-values are going to change. It might be the p-values of the other non-significant predictors can change as well. In order to determine if we can drop a set of variables, you need to perform the partial F test. So this is more of a topic for the take-home exam, but something to keep in mind for the in-class as well. You're only allowed to drop one variable at a time. All right, standard errors in multiple regression, a bit more complicated. How far off are our estimated coefficients likely to be from the truth? Well, the formula is actually pretty similar to simple linear regression. However, there's an additional component, this 1 minus Ri squared. Ri squared is the value of R squared that you would get if you tried to predict Xi from the other predictors in the data set. So if you can predict Xi pretty well from those other predictors, that means that the amount of information contained in Xi is fairly redundant with the other predictors. And when that's the case, when the information provided by Xi is fairly redundant, the standard error of Xi in the model is going to be fairly large. So if Ri squared is large, Ri can be predicted well from the other variables, and so the standard error associated with its coefficient is going to be large as well. Why does this make sense? Well, remember what that coefficient is telling you is it's saying, okay, imagine two individuals that are completely identical in all regards, except for that one particular Xi, that differs by 1 unit. Well, if Xi can be predicted from the other variables in the model, there's a lot of correlation going on. There aren't really two individuals that are identical except in terms of Xi, so it's difficult for the model to really isolate the association between Y and Xi. Everything's changing at once, so it's hard to tell, well, what would happen between two groups of individuals who are identical in all other regards, but are different in only Xi by 1 unit. Those individuals don't really exist. So the more correlation in your data set, the larger the standard errors of those coefficients are going to be. All right, the variance inflation factor helps to gauge whether or not the standard error has increased a lot due to the correlation. And so we can look at 1 over 1 minus Ri squared and look to see what that VIF is. So the square root of the VIF tells us the factor by which the standard error has increased due to correlation. So a VIF of 5 means that the standard error for that coefficient is 2.2 times larger than it would have been had the x's been independent. How do we know when the variance inflation factor is large? Well, we calculate 1 over 1 minus R squared, where R squared is the value of R squared for the regression, not R squared adjusted. If the VIF is bigger than this quantity, we say that that VIF is big, and that correlation is rearing its ugly head. It doesn't invalidate the model, it just says the standard error is bigger than it would have been had the predictor has been independent. So key thing, multicollinearity doesn't invalidate the regression model. It just says that your coefficients aren't all that well estimated. There's a lot of uncertainty associated with them. In descriptive modeling, that's kind of a bad thing because we want to estimate the coefficients as well as possible, but it doesn't invalidate the model. It still might be useful. All right, so I have a few extra slides kind of giving an overall review. I'll let you guys review those on your own time, and that is it. Good luck studying, and I will see you guys later this week.